Hello students. So today in this lecture, this is our lecture 5 of the physics course, and in this lecture we will study the concepts of distance, displacement, speed, velocity, and speed velocity graphs. So we will be studying the graphical analysis as well. So starting now from distance. So what is distance? Distance is the total path that is traveled by an object. So distance is a scalar quantity and it just uh, shows the total path that is being traveled by the object, and this is always and always positive. Distance will be always positive, right? And we can represent distance by the symbol S. So the symbol S is used to represent this quantity. This is a scalar quantity represented by S. Now displacement. So what is displacement? Displacement is the shortest straight line distance from start to end with a direction. So from this we can say that displacement will be the shortest distance in a straight line from point A to point B. Alright, so this is the basic difference. Distance was just any path traveled from path A to path B. This is distance. We can call this is also distance moving from path A towards this path B. Alright. Sorry, moving from point A to point B. So this is distance. But displacement will be the shortest distance. So the shortest distance between two points A and B. It is going to be this in a straight line. So this is displacement, and of course displacement is a vector quantity. This is a vector quantity because this is a specific direction. We can see from A to B the direction is this way. So it has a specific direction, while distance has no direction. From A to B it can be either this path, through this path, or it can be through this path, or it can be through any other path. For example, this path. Let's see. So distance has no direction, so it is scalar and it is always positive. Displacement has a direction, so it is vector quantity. And we can represent displacement by the symbol S with an arrow above it. Okay. Now, distance versus displacement. We can see it from here. This is our point A, this is our point B. So moving from point A to point B, this is basically distance. The length of curved path is the distance. But the displacement will be this from point A to point B. So this is displacement. This is distance. Okay, this is distance and this is displacement. Okay, now we are comparing both of them. So distance is a scalar quantity while displacement is a vector quantity. Depends on path. Distance, yes. Displacement, no. Because displacement does not depend on path. It will be the shortest path. And distance is always positive, while displacement can be negative, positive, or zero. We can have zero displacement. For example, if a body moves from this point, it moves from here and here and here and here, and then it comes back to this point. So it has covered some distance, right? So distance will be positive, but in this case, the displacement is zero because the object moved. No, the object moved, yes, but it came back to its original position, to its starting point, so displacement is 0. Alright, relationship distance is always greater or equal to displacement. Okay, now we have a example. A student walks 40 meter towards east, and then he moves 30 meters towards west. Alright, so we can make it like this. This is north, this is south, and this is east, and this is west. So students walks 40 meters towards east here, and then he walks 30 meters north. So 30 meters north from there we can have this point, right? So he moves here and then he moves here. So distance is 40 plus 30 is equal to 70 meters. But displacement can be calculated from here, like this is the total displacement from here to here. So using the Pythagoras theorem, we can say that 40 square plus 30 square under root is equal to 50 meters. So 50 meters is the displacement covered, because displacement is always in a straight line. So we can say that this was the displacement. He moved 40 meters in this direction, in east direction, this is east, and then he moved 30 meters in this direction towards north. So this is the final point. So from this point to this point, this is our displacement, which is 50 meters, while the whole of it, this is 70 meters, which is distance. All right. So displacement 50 meters is clearly less than 70 meters actually walked. Now speed and velocity. So the rate at which distance is covered is called speed. So if a body covers, an object covers a distance of 30 meters in 3 seconds, so if we divide the total distance covered by the body by the object divided by total time taken, we can find the speed of that object. So this is a scalar quantity, alright, because distance is scalar and time is also scalar. So it is a scalar quantity and it tells us how fast the object is moving. It does not give any information about the direction. Alright, velocity. Now, how is velocity different from speed? So velocity, basically it is the rate of change of displacement. So it means that velocity will be a vector quantity, because displacement is a vector quantity. So we can say that if we divide the total distance covered by the total displacement covered by an object divided by the total time taken by that object, this will be the average velocity of the object. So it tells us about how fast the object is moving and the direction in which the object is moving. So average velocity is equal to total displacement divided by total time. This is the mathematical form for both speed and velocity. But for speed, v will be scalar with no arrow above it, and s is representing distance here in case of speed. But if it is velocity, then it will have an arrow over it like this, and s will have an arrow as well, because for velocity it will be velocity is equal to displacement divided by time. And instantaneous speed or instantaneous velocity is, if we take the time interval very small, so we can say that that will be the instantaneous speed or instantaneous velocity of that object. So instantaneous value is equal to at one instant of time, such that time reaches the total time taken reaches to the value 0. Okay. Next, we have some graphs here, graphical representation of velocity. So this is an interesting graph. First of all, we should know that the slope of this position and time graph, it always gives us velocity. Alright, slope means the position divided by time. Alright, so velocity is equal to the slope of xt graph, or we can say position time graph. So velocity is equal to the slope of xt graph is equal to delta x divided by delta t. Means that the change in position divided by the change in time. So if we look at the graph, in the first graph, this is our first graph, okay? We can see that the time is ticking, the time is moving from 0 seconds to, let's say, 10 seconds. So in these 10 seconds, the object is not changing the position. There is no change in vertical direction. The object position remains the same because you can see the time is ticking, the time is traveling, but the position is not changing. It is not changing. So if the object is not changing its position while the time is ticking and the time is moving, so we can say that the object is at rest. Alright, so this graph shows us that the object is at rest. Okay, now this was graph 1. Now we will look at this second graph. Okay, this is graph 2. The graph 2 shows us that as the time is passing by, the position of the object or the distance covered by the object is changing as well. So in first second, it covered a distance of, let's say, 1 meter. Then the next second, again it covered a distance of 1 meter, and so on. In the third second, again it covered a distance of 1 meter. So this shows us that in each interval of time, the object position is changing linearly. In each and every second, it is covering, for example, a distance of 1 meters each. So we can say that the object is moving with uniform velocity. The velocity is not changing because why? Because in each and every second, it is covering the same amount of distance. We can see it from here. In first second, it covered a distance of 1 meters. In the second again, it covered a distance of 1 meter. And in the third second, it covered a distance of 1 meters, and so on and so on and so on. So this is uniform velocity. Okay, now what is happening in the third graph? The time is moving, but initially the object is covering, for example, in the first second, the object covered almost zero distance. We can see here in the first second, there is no change in the y direction. The object position is almost not changing. So in the first second, the object was almost at rest or very low velocity. Then in the next second, it covered a distance of 1 meter. In the next second, it covered more distance, and then as the time passes, it is covering more and more distance. So we can say that the body is basically increasing its velocity. The velocity of the body is increasing with time. Here, the velocity is not increasing. Here, the velocity was same because same distance was covered in each and every interval of time. So the velocity you can say is same. But here the velocity is increasing because the distance covered in each interval is increasing. So we can say that the body is accelerating. The body is accelerating. So this is a graph of uniform acceleration. Here, what happens as the time goes by, initially the body is accelerating, this velocity is increasing, but finally from this point onwards, what happens here is that the body slows down. The body slows down from here, and then as the time passes by, the body comes to rest. You can see that here the body comes to rest. It's not changing its position. So it was moving fast, and then it slows down and stops. So this is an example of retardation, or we can say negative acceleration. All right.